Homework 13, section 7.1, the standard normal curve, video 4. All right, it's time to actually get to the standard normal curve. But before we get to the standard normal curve or the standard normal distribution, we need to talk about just a normal distribution without the word standard. A normal distribution is what most people commonly know as a bell curve. So it's easy to spot. Starts really low, gets high, goes back down, but there are some properties about it. Number one, the mean is in the center, and it's symmetric, meaning that the left and the right half are mirror images of each other. Number two, the mean, the mode, and the median are all equal to each other. Number three, the empirical rule still applies. We'll get back to that in a second. And number four, the tails technically go forever without actually touching the axis down here. In algebra, it would be the x-axis, but it can be any axis you want, actually. The reason the tails go forever without touching is based on the calculus behind the statistics. Algebraically speaking, there is an equation that draws this curve. You really don't want to see it. If you want to see it, send me a message and then you'll regret asking. But based on that equation, this graph has what are called asymptotes, which is a line that the graph gets closer and closer to but never ever touches. So technically these tails go forever. But let's go back to the empirical rule for a second. Recall that if you have a bell-shaped curve, approximately 75% of the data was within one standard deviation of the mean. So if this distance is the standard deviation, which we're representing as sigma, then one standard deviation to the right is mu plus sigma, and one standard deviation to the left is mu minus sigma. So the total area between here, these two strips in the middle, equals 75%. Because of the symmetry, each of these has the same area, half of 75%. So this area would be 0.375, and this area would be 0.375. Because if you added both of those, you would get 75%. The second part of the empirical rule said that between two standard deviations to the right, so mu plus 2 sigmas, and two standard deviations to the left, you pick up 95% of your data set. So these two extra strips, number one, have to be equal, and number two, have to bring the grand total to 95%, or 0.95. I forget what it was exactly, but I'll figure it out. If I take 0.95 and subtract the 75% in the middle, something's not right. I don't know where I got 75% from. The empirical rule never said 75%. I know what I was thinking. I was thinking Chebyshev's theorem, but don't worry about that. So I recant. The empirical rule says that between one standard deviation to the left and one standard deviation to the right, there's 68% of the data approximately, and half of 68% is 34%, or 0.34. What I said about being between two standard deviations to the left and two standard deviations to the right was correct. That total was 95%. So to find the area of each of these second strips on the left and on the right, I have to take the 95% that they encompass, subtract the 68% in the middle, and then divide the difference by 2. So the strips between 1 and 2 standard deviations on either side is 13.5% or 0.135. Again, that gives us 68% within one standard deviation and 95% within two standard deviations. And you'll recall that the textbook, well, actually the textbook used to say about all of it, but now they're saying 99.7 like I used to. So, within 3 standard deviations of the mean, so mu plus 3 sigma to the left, mu minus 3 sigma to the right, that's 99.7% of the data. So to find the area of these third strips on either side, I'll take 99.7% subtract the 95% that's already represented here, and then divide that by 2. And what we get is a very small decimal. I'm going to draw some arrows here. This area between 2 and 3 standard deviations to the right is a measly 0.0235, and the area between 2 and 3 standard deviations to the left is the same, 0.0235. And then we could even find the remaining area on the 2 tails. The tail to the right of 3 standard deviations to the right, and the tail on the left of 3 standard deviations to the left. By taking the total area 100%, subtracting the 99.7% that's already represented, dividing that by 2, and the area we get for this right tail is a measly 0.0015, and because of symmetry, it's the same over here. If you just remember that the 3% in the empirical rule are 68%, 95%, and 99.7%, this can be recalculated. Just reminding you that the empirical rule still holds. And in the context of probability, we can now represent the empirical rule in terms of probability. The empirical rule